Hello and welcome to Statistics, an Unreliable Friend. First of all, thank you so much for having me at Data Platform Summit 2020. Let's begin. Few words about me to begin with. My name is Magnus Ahlkvist. I am 44 years old. I am from Sweden. I've worked with SQL Server for many years now, 21 years, I'm not sure exactly when I started. I'm an independent consultant with my own company, Transmocopter SQL. And as of 1st of October this year, I am a data platform MVP from Microsoft. I do a lot of community organizer stuff. I speak for user groups. I am on the board of my own user group in Sweden. I am an organizer of SQL Friday, a weekly event running every Friday. And I am one of the organizers of Data Weekender, one of the first virtual conferences that was organized beginning of this COVID-19 situation that we have been facing for, too long, to be honest. My contact details are on the slide, so let's jump into the actual presentation, which I assume is what you came for. Oh, by the way, I do this presentation recorded before the conference, so I am in the chat as you watch and listen. So if you have any questions, just type them in the chat and I will be happy to answer your questions as we go along. Okay? There are three kinds of lies. Lies, damned lies, and statistics. This is not a Mark Twain quote, although he's been credited for it. But we're going to talk about statistics today. And statistics in SQL Server. How is SQL Server using statistics to come up with the sometimes amazing query plans and sometimes not so amazing query plans that SQL Server does come up with. So it's going to be a little bit about the optimizer and a lot about statistics. So why did I make this presentation to begin with? Well, I was working for Statistics Sweden, the Swedish Census Bureau. We were doing we were creating a system for gathering and crunching and reporting on financial statistics and mainly debt-related financial instruments. So we got data in, we crunched data, we sent data to the European Central Bank, and we published data. And we had really limited time period to crunch the data, because we got some input. The largest input we got was sent to us on something like the 4th bank day of the month. And then on day 6 we had to publish preliminary results to the European Central Bank. That was quite a tough deadline. And we got some performance problems on the reporting to the European Central Bank. So it took hours to run a report, which normally ran in seconds. So that was a bad situation. We were late with our preliminary reporting. Users were upset. They yelled at me, and I was sad. Basically, that's the situation. So I came up with a solution that I called the Voldemort solution. I'm not going to demo it, but I'm going to talk you through it a little bit. But it got me looking more into statistics, and specifically a problem called the ascending key problem, which I will go into the details of in this presentation as we go along now. So you don't want to sit here and wait for hours for a query to run. So instead I created a very small order database It's super simplified. It has some order header information, it has warehouse locations and customer locations. And I'm running a query which will calculate the average distance from the warehouse to the customer address for a given day, basically. And I'm going to start this off in SQL Server 2008. You know it's not supported, but I think it's a good idea to start there anyway, and then we will look at the evolution of the way SQL Server handles statistics and row count estimates in later versions as well, but we will start in 2008. And why 2008? Well, that's when I was working on this system. We were using SQL Server 2008. So I think it would make sense to start back there. And as you will see, there is a big difference between 2008 and, well, let's say 2014 and later. So I'm going to start with a short demo to show you the characteristics of our performance issue. So I'm now in the stats demo database, which is a demo database created just for this presentation, containing a few tables, which I told about before. It's an order header table, it's a warehouse table, it's a location table, and it's a customer address table. Basically, that's it. I have done an update statistics prior to running this, so the statistics are perfect. SQL Server knows everything there is to know about my data. And I'm enabling statistics IO and statistics time to be able to look at the number of reads SQL Server is doing and the CPU time spent on executing my query. Okay, so we're starting with a query that looks for the average distance between warehouse location and customer location for the orders for a given day, namely the 24th of August 2016. So I'm going to run this query, and I'm going to jump into the execution plan. And just note here, we got the clustered index scan of the customer address table as the first operator in this execution plan. Normally, when you look at a query and you see clustered index scan, that is not always a good thing. In this case, it actually is, because the customer address table is a small one, and it's much more efficient to just read that table, the whole table. Same thing with the locations table. It's a small table. It's just 5,500 rows. Just read everything, do a hash match between them, and then much later in the plan, that's when we start to look at the actual orders for that day, and then join them in. And the reason being, this returns 12,500 rows, so it makes sense to just run that part late in the plan, get everything set up, and then just merge in the orders, or in this case hash matching the orders into the customer address and the locations table. Now, in a very normal order system, you have this kind of setup. You do your batch windows, you do your maintenance of indexes on a nightly basis. You can't do that in the middle of the day because it kind of disturbs the actual operations of the system. So you have your maintenance window, then you get the orders the next day, and by noon or by end of day or sometime in the day, you need to ship your orders from your order system to the warehouse system. And that's when we run into problems, which we will see now if we run the same query as above, but with 25th of August, for which we just created a couple of orders, or 12,500 orders. So we run it. It's still kind of quick because the data volume is small. But if we now look at the execution plan, we see a different shape of the plan. We see that SQL Server decided to start with the index seek on order header. And if we look at this line, we see that the actual number of rows is 12,500, just like the day before. But the estimated number of rows is now 1. And because SQL Server thinks I'm just going to get 1 row back from the database, or from this table, it then decides that reading in the customer address for that 1 row, well, let's do that with an index seek, and then send it to a nested loop join. A nested loop join means that this is kind of the driver of the nested loop join. For every row in the output of that operator, run this operator. And if we now look at the messages pane, and we see that customer address, we have a scan count of 12,496. So instead of reading that table once, SQL Server is reading that table 12,500 times, doing 50,000 logical reads. That's not a good situation. It's actually a pretty bad situation. And if your data volume is a lot larger, then this problem is going to scale. It's going to be worse than in this scenario. I mean, this is still pretty quick. But if we go back to the execution plan, even with this small amount of data, we get this little fella, a sort operator introduced late in the plan, with an estimated number of rows being 1 coming into the sort. You know, if you get 1 row and you try to sort that, that's going to be a quick operation. But if you get 12,500 rows, well then SQL Server has estimated a memory grant for the sort operation based on 1 row. And it got 12,500 rows. So that sort operator is spilling to tempdb. Oh no. We get physical I/O. And no, this is not a good situation. We can see that we're spending 625 milliseconds on the CPU. We didn't spend hardly anything on the query before. Let's have a look at the difference. Messages, and let's go down here. Well, 266 milliseconds on the CPU, so it's 3 times as much time on the CPU. Not good. Let's dive a little bit more into why it's slow. And yeah, it's the statistics. It's all lies, right? But let's look at what SQL Server looks at when creating the query plan. So let's look at demo script, the cause. And by the way, these demo scripts and the presentation, they are on my GitHub. So just look at Transmocopter on GitHub, and under presentations you'll see this presentation among with other presentations that I've done. So I'm gonna use a command named dvcc show statistics, which is kind of what SQL Server does when trying to come up with a query plan for a query. So I'm running it for the sales order header table and the index ix_order date. So what can I see? I see on the first result set, I see when the statistics were updated, how many rows are in the table, or how many estimated rows are in the table, how many rows were sampled when I created the statistics or updated statistics, and I used a full scan, so all the rows were sampled. How many steps are in the histogram? We're going to look at the histogram soon. What's the density? We're going to talk more about density soon. And so on. But really what I'm interested in is just the histogram. So we can run dbcc show statistics with histogram. And then we only get the statistics histogram. And what this contains is a data set with some key values from my data in the table. Some information about how many rows have values which are between one key and the previous one. And then how many rows have exactly the value of that key. That's basically the information we need to look at. The average range rows is the average number of rows per value between two steps in the histogram. And then distinct range rows is how many distinct values do we have between two steps in the histogram. So using this information, SQL Server can make a really good guess most of the times on how many rows will be returned by a specific search predicate on the table. Now, if we move down to the very bottom of the histogram, we will see that the highest value for order date that SQL Server knows about in our table is August 24th, 2016. But we all know we introduced 12,500 rows with August 25th as the date. But SQL Server doesn't know about them because SQL Server knows about the data distribution in the table as of the last statistics update command. And when we ran statistics update, we only had August 24th in the table. So this is why SQL Server comes up with a really bad execution plan. You can't really blame SQL Server in this case either. There is no way the SQL Server optimizer can know about this data from August 25th if we don't run an update statistics. And running update statistics on a large table is going to cause a lot of I/O. It's going to take time. So we don't want to put our system under that kind of pressure in the middle of the day. And that's why we normally as DBA schedule our statistics maintenance to run outside of working hours or outside of, let's say, business hours in the system. Statistics density vector, you saw that in the output from dbcc show statistics, you saw some information about density. And the density has to do with the number of distinct values versus the actual row count of the table. So density is defined as 1 divided by the distinct number of values. So in our case, the density for our index ix underscore order date is going to be 1 divided by the number of unique order dates we have in our table. Some other examples of information you could have in your database. Gender, for example. It would have a very high density. And if you look at social security number, that's a typical low density column because every person has a unique social security number. So if you have heard about selectivity, a query with a low selectivity or a column where you run queries with a low selectivity is usually a high density column. So let's say you query for all the males in a population in a person table. Well, that will be a low selectivity query because you're running it against a column with a high density. This is going to be more important in later versions of SQL Server. The estimated row count of a table, or of a predicate I should say. When SQL Server is using the histogram, it's very easy, because let's say in our case order date 24th of August 2016, SQL Server will look into the histogram and find, okay, we got 12,496 rows with that order date. And then the optimizer will create a query plan based on that row count. When looking at August 25th in the histogram, SQL Server didn't find any rows. That wasn't even a step in the histogram. And therefore the optimizer or SQL Server will estimate 0 rows, or actually will always estimate 1 row, because otherwise it would be an empty query plan. You always have to have a row to run the subsequent steps in a query plan. If SQL Server would have used the density vector instead of the histogram to come up with a row count for our table, it would look at the density for the columns involved in the equality predicate. So that means when I query for order date equals some date, it's going to look at the density of order date and see that, okay, the density is 0,004. And then it will look at the row count, the total number of rows in the table, and so the estimated number of rows for the equality predicates against the order date column would be the density multiplied by the total row count. So that would be 12,497 for August 24th. And it would be 12,497 for August 25th as well. And then in later versions of SQL Server, we got the new cardinality estimation, and that kind of turned some of these things upside down. But let's look at how it looked in 2008. If we could just get SQL Server to use the density vector, we would be at least okay. But you can imagine if I would query for August 26th where there was actually no data, then SQL Server would still have started with a clustered index scan on customer address and a clustered index scan on locations, and that would be completely unnecessary because there were no customer orders to match these addresses and locations with. That's the whole reason why SQL Server chooses another query plan when it estimates few rows from the order header table based on the order date predicate. So what we have here is what's called an ascending key problem. It means we have an ever increasing key value in an index. Whenever we run statistics update, it's not going to be good anyway, because the next row that comes into the table will have a higher value, a value that falls outside of the statistics histogram. So SQL Server really can't ever come up with a good execution plan. Sometimes we can get bad estimates even with perfect statistics, but let's first focus on the ascending key problem, because that's the problem that this whole session is based on. So we're going to look at some suggested solutions to work around the ascending key problem. We have statistics IO turned on, we have the execution plan turned on. So the first thing I'm going to try is to parameterize the query. So instead of hard coding order date into the dynamic SQL, I'm introducing a parameter in the dynamic SQL. And then when I execute the query with sp execute SQL, I have my statement as before, but then I also add the parameters into it. So let's run this for August 25th to begin with. Execute. Oh, my connection is broken. That's no problem. Let's just run use.demo, get a new connection. Now we need to set statistics IO and time on again. We still have the actual execution plan on. And let's rerun the query. So what kind of plan would we guess? Well, it's August 25th. We don't have the statistics for it, so let's have a look. Yeah, we got the bad plan. We start with an index seek on the order header table. For each row returned, we do an index seek on the customer address table. We have the warning on the sort with the spill to tempdb. And under messages, we have a high scan count on the warehouse table and on the customer address table, and it's bad. Let's move on. And now let's run the query for August 24th, also with the parameterized query. And what? No. We got the bad plan even for the date that is in the histogram. Why? Well, the reason is that we have caught a bad case of parameter sniffing. That means SQL Server creates an execution plan based on the first execution of a query. It looks at the parameters for the first execution of a query, and in our case the first execution was August 25th. It then creates and keeps the query plan that came up, that SQL Server created, with August 25th as our value for the equality predicate on order date. And it keeps the plan. So the next time I'm running a query, SQL Server is just going to look at this part of the query, where oh.orderDate equals the parameter dt. And it doesn't look at the value of the parameter because it just sees, oh, I already have a query plan for this query. So let's reuse that one. If we would have reversed this and started with August 24th, we would have got a good plan, which would have been reused for the order date that previously created a bad plan. But now we didn't. So this is not a fail-safe solution, to say the least. Let's move on. We could trick SQL Server by getting the date from a function. So we declare our date. We still have a parameterized query, but instead of doing our equality search against a parameter, we do it against a function, which is the most stupid function you could think of. It's a scalar UDF. It gets a date as input. It then returns that date. But the funny thing is, SQL Server Optimizer, at least before SQL Server 2019, when seeing a scalar UDF, it has no idea about the contents of that UDF. It's just going to run it as if it was a black box. So let's run this query. And now we get this execution plan that we want. We got the clustered index scan on customer address, the clustered index scan on locations, and then the hash match to match the orders into the address information. Perfect. But really, the this doesn't really look good. And if I show this to a developer that doesn't know the background of why we use this function, he or she would look into, okay, we run this gallery UDF. Let's look at what it does. It does nothing, it just returns the input. Okay, let's refactor and remove that function call. There are other ways to solve this. Back in 2008, one solution was to use trace flag 2389. A trace flag in SQL Server is kind of a feature toggle. You turn on a trace flag to switch on a specific behavior in SQL Server. And trace flag 2389, what it does is it looks at your past 3 or 4 statistics update on an index. And if it can identify that you have an ever increasing value for the key column, it will mark that statistics object for the index as an ascending key and then change its behavior in coming up with an execution plan in the way that if a value falls outside of the density vector, if a value falls outside of the statistics histogram, SQL Server is instead going to use the density vector instead of coming up with a one row estimate. So let's do this, and this is going to take a little while. Let's first switch on the trace flags, and then we need to start with an initial statistics update. And then what I will do is create 50 orders for August 26, update statistics, create 50 orders for August 27, update statistics, August 28, update statistics, and August 29, update statistics. So that's 4 subsequent statistics updates, which should mark the column as an ascending column. And this, as I said, it will take a little while. In the meantime, I'm going to tell you about the other trace flag that I also enabled, 2388. What that trace flag does is changing the output of dbcc show statistics so that we will see if a column is marked as ascending or not. It doesn't change any other behavior of SQL Server, it's just the output of dbcc show statistics. It also has an interesting side effect. When trace flag 2388 is enabled, we cannot any longer look at the statistics histogram. I don't like that, but that's how it is. So now I've done my fill data, update statistics, etc. And now we can do dbcc show statistics for the ix_order date index. And we see that it is now marked as ascending. And let's try to add orders for, well, let me just show you this first. We're going to run dbcc show statistics with histogram, and we don't get a histogram. So to see the histogram, we need to do dbcc trace off, just switch off trace flag 2388. And now we can see the histogram. So I'm now going to create some orders for August 30th, which will still be outside of our statistics histogram. And the reason why I wanted to switch off trace flag 2388 is to show you that the value is outside of the histogram. And for some reason it takes some time to create orders for August 30. Now it's done, and we can see at the very bottom of the histogram that the highest value for order date that SQL Server now knows about is August 29, but we just added some actual orders for August 30. So let's run this query, Same query as before, but with August 30 as the date. And look at the execution plan, and we get the good plan even when the value is outside of the statistics histogram. So this is the solution for SQL Server 2008, and I think even SQL Server 2012, which by the way is still supported. So you might be running SQL Server 2012. But we're not going to stay on old versions of SQL Server. By the way, the solution I implemented as a kind of panic reaction was what I call the Voldemort solution. The reason I call it the Voldemort solution is I don't really want to talk about it. What I did was running dbcc show statistics, look at the highest value, then run an actual row count of, or get the max value in the table, look at the row count of the max value, and compare it to what I had in the histogram. And if it was off by too much, something like 500%, then I would do a statistics update. And that job was running, I think, every 5 minutes. So it's really a brute force method, which I don't recommend you to use. Let's try something else. Let's upgrade to SQL Server 2014, and in our case I'm running this on SQL Server 2019 database, I think. So I'm just going to do a change of compatibility level from 2008 to 2014. And we're going to run the query again. And we're going to see another plan shape. We see a sort with spilt attempt DB. The cost 0, I think that's the estimated cost. The actual cost of this sort operator is actually more than 0% of the query plan, but let's not care about that. We have here an index seek of order header, and then we have a clustered index scan on customer address, and then hash match. Well, it's a decent plan, I would say, but we introduced this sort operator. And you see an estimated number of rows in this picture being 1,774. So it's not 1 anymore, but it sure isn't 12,500 either. That is our actual row count for the date we're searching for. So we're going to look some more into that on the cardinality estimator demo in the very end of this session. But just have these figures in mind. Let's upgrade to SQL Server 2016 and see if it changes anything. Well, no, it doesn't. It's still kind of bad. Let's upgrade to SQL Server 2017 and run the same query. No, same plan as in 2014. And to me, this is worse than having to enable a trace flag, because it's a row count that is still too low for SQL Server to come up with a good plan. It's so far off from the actual row count. It's almost like 1/10 or something of the actual row count, or 1/8. We could use SQL Server 2019, and we can run the query. And still a bad plan. I think if we run the query a couple of more times, we at least get a better memory grant for the sort operation, because we have this adaptive query processing, which will kind of mark this query plan with last time I ran it, I got a spilt attempt TB. So next time we run it, let's try to increase the memory grant on this specific operator. But it is still not a very good plan. So what more can we do? Let's skip these through and skip to the very end here. Here we go. We could use something called optimize for unknown. So we're going to go back to SQL Server 2008 compatibility level first, and then we can introduce option optimize for the date parameter unknown, and that forces SQL Server to look at the density vector instead of using the histogram. Oh, we need to have a date that actually has some values. 30. So what do we get now? Well, we get the good plan again. And then we can go back to, for example, SQL Server 2017 and see how SQL Server behaves in a later version with optimize for unknown on the as a query hint. And yeah, that in this case it actually works the same in SQL Server 2016, 19, 17, what have you. You have the same behavior in any version of SQL Server that you run on. So that's optimized for unknown. In this case, it's a decent idea to use optimize for unknown because our data distribution in the table is very even. In other cases where you have a super uneven data distribution, it might not be such a good idea, because for some predicates you want one plan, for some other predicates you want some other plan. And then you perhaps would need to introduce, for example, option recompile, which is kind of a brute force method too. Or if you know when you write the query or when you run the query that for specific values I'm going to get a low row count, and for some other values I'm going to get a high row count, you could use a trick to introduce, for example, a comment in the code, high or low, and that would create different query plans for those two queries. Even though they are actually identical, they will get a different query hash based on the query text because of that comment. So is optimized for unknown a silver bullet? Well, it depends. There are no silver bullets, to be honest. In this specific case, optimized for unknown is the silver bullet. But for another query also suffering from the ascending key problem, well, it might not be. So I mentioned that we would look at the cardinality estimation, and we have looked at the ascending key problem, but there are other causes for a bad estimate from SQL Server. You could have statistics updated with a low sample rate, which we would typically do if you have 50 billion rows in a table. You're not going to want to do an update statistics with a full scan every night, because that's going to take a long time. So if you have statistics updated with a low sample rate and you have a very uneven data distribution in the table, well, then SQL Server might miss some values and build a bad histogram because of that. You could have bad cardinality estimation due to complex predicates in the where clause or in an on clause of a join. And we're going to look a little bit at that in a demo. SQL Server 2014 and later addresses the ascending key problem, but as we saw, it didn't do it with huge success, at least not every time. So let's look at our final demo, the cardinality estimator. And in this demo, I'm introducing a new table, which I call cars. And what I'm going to demo first now is the cardinality estimation when I have a more complex logic, more complex predicates than just one equality search. So first I'm going to fill this table with some data, and what I'm going to do is add some models and brand names and some colors on cars. Not that many different values. We can start with SQL Server 2012, and we can look at the kind of what have we in the table. We have all the cars with brand name Volvo. Well, that's one row count. I think it's 7,000 rows. We have all the cars with the model name V70. Well, that's 5,000 rows. And we have all the red cars. And that's 2,270 rows. We could look at the statistics objects in DBO cars with SB help stats. And because I ran these three queries, SQL Server automatically created statistics objects for me, because it needs statistics. If I don't have any statistics objects on a column, SQL Server is by default going to create statistics objects for me, because the database option auto create statistics is by default turned on, and I think that's a decent idea. So I have these statistics object that we're going to look a little deeper into. They're going to show the distribution of brand, model and color. So we see for brand we have Saab and Volvo. That's our brands. We have few Saabs, we have many Volvos. For the models we have a few Saab 9.3s, or 9.3s is the only thing SQL Server knows about. We have S40s, 2,000 of those, and 5,000 V70s. And for the colors we have black, blue and red, with few, a high number and a medium number for that color. So just to show you what kind of data distribution we have in our table. So if we would ask SQL Server how many Volvos do we have, then SQL Server would estimate 7,000 and then build us a query plan based on 7,000. So if we would ask SQL Server how many Saab V70s do we have, so brand name equals Saab, model name equals V70. I know that V70 is a Volvo model, so I would estimate 0 rows. SQL Server doesn't know that much about cars, so all it can do is look at 5,000 V70s and 796 Saabs, and then try to come up with an estimate for the combination of those predicates. So let's look at the estimate for a Saab V70, and I'm going to do that with the estimated. I don't see the icon for it, but Control L is going to give me the estimated execution plan. And we're going to look at the estimate from this clustered index scan in the beginning. And the estimate is 510 rows. Where did SQL Server come up with? Did I say 510? Well, it comes up with that because of the combination of the number of Saabs in the database and the number of V70s in the database compared to the total row count of the table. If I look at Volvo V70, then the estimate is going to be slightly different. It's going to be 4,489 rows for the combination of Volvo and V70. And that is because Volvo, well, SQL Server knows that there are more Volvos than Saabs in the table. Let's look at this. How many red Volvo V70s do we have? Estimated 1,307. We can run the query and it's going to be 0. But since the brand name, the model name and the color are in different statistics objects, we don't have a combination of them in a statistics object. There is no histogram that can combine different columns. A histogram is always for one column. So that is the information SQL Server has when it tries to come up with an estimate of this more complex predicate. So what's the formula? How is SQL Server thinking when it comes up with an estimate? In the old cardinality estimator, which was what you had prior to SQL Server 2014, it would be the estimate for the first predicate multiplied by the estimate for the second predicate divided by the row count multiplied with the estimate for the third predicate divided by the row count, etc., etc. So in the case of Volvo V70 with the color red, the estimate would be based on 7,000 Volvos. 7,000 Volvos multiplied with 5,000 V70s divided by the total row count of the table multiplied with the number of red cars in the table divided by the total number of rows in the table, which would give us 1,307. And we know we got 0 as the actual, but this is the formula SQL Server will use. And to be honest, most of the times it's good enough. If we now upgrade to SQL Server 2014 to get the new cardinality estimator, we can run the same estimation, Volvo V70 with the color red. And now the estimate is 1,769 instead of 1,307. I mean, it's the same ballpark in this case, but it's not the same. So it's a new formula. And the new formula is selectivity for the most selective predicate. The most selective predicate in this case, I think, is the color red. And then it's going to be multiplied with the square root of the selectivity for the second most selective predicates, multiplied with the cubic root of the selectivity for the third most selective predicates, etc., etc., and then multiplied with the row count of the table. So in this case, number of red cars divided by the number of rows multiplied with the square root of the 5,000 V70s divided by the rows. This, by the way, is the selectivity. It's the estimated rows for a specific value divided by the total row count. And then we have the cubic root of the selectivity for the 7,000 Volvos multiplied by the row count. And why this change of formula? Well, in the people who are responsible for this formula at Microsoft, the math guys, I would say, they came up with the idea that in a table, columns are usually related. And in our table here, we have a relation between brand and model. So it makes sense to get these two related. But the color is unrelated to the model and the brand. So it was a good idea to do it for the model and the brand. It was a bad idea to do it for the color. But you have to have a rule that is applied to all the columns, basically. We can run this just to see that the math adds up. 1769, and if I would look at the estimated row count again, I would see 1769. So yeah, the formula is what is actually used by SQL Server. If we go back to the orders database and the estimates that we got from when we upgraded the SQL Server 2016, the way SQL Server was handling the ascending key problem. It is kind of a complex decision tree, but what SQL Server would look at is the density multiplied by the total row count and the square root of the total row count, and it will use the lesser of these values. And in our case, the density multiplied by the total row count is 12,500 rows. But the square root of the total row count is just 1,700 rows, so that value is going to be chosen. And I have no idea why SQL Server picks that value or why that decision is made in optimization. But that's just how it's done. And that's why we actually got a worse estimate than we would have had in SQL Server 2008 with trace flag 2389. So, when Microsoft released SQL Server 2016, maybe you remember they said SQL Server 2016, it just runs faster. In this case, it actually didn't. But it's an edge case, you might think. But I'm not so sure that it is an edge case, because the ascending key problem has been there forever. And trace flag 2389 is enabled in many scenarios. And trace flag 2389 has no effect in SQL Server 2016. So you can't force that old, much better behavior that you got with trace flag 2389. Thank you for that, Microsoft. Anyway, that is the end of this presentation. So I want to thank you all for joining me. I'm going to stay in the session for a while and answer your questions if you have any. And thank you to the sponsors of this conference, of Data Platform Summit, Microsoft to begin with. We wouldn't be having this conference at all if it wasn't for the products that Microsoft released. And you have heard me talk about some odd behaviors and bad decisions that Microsoft has made with SQL Server, but I mean in general it's a fantastic product. So thank you, Microsoft, for creating SQL Server. That is all I have. Thank you.